Yeah, so it's time for our last discussion and to close the meeting. Today, I'd like to thank Eric Rosolowski and Carl Warnick, who are online. There's Carl. And Kevin Bandura is in the room. We're not going to make him sit up front today. He's the sole. Jim did it. Yeah, there's no pressure. It's easy going. So Eric is online. We're not seeing your face on the big screen here, Eric, but that's okay.
He's behind you.
He's behind you.
Well, that's Carl. Eric is also online, but we're not seeing his face right now. That's fine. And of course, this is meant to be an open discussion. The panel is only a general suggestion. Hey, Eric.
Hello. I just had a little coffee spill, so I'm up for a minute. So yeah, I'll be here in a minute.
Okay. Well, we can start. So the title of the discussion is "What is the next step for scientific instrumentation at K-band with the GBT?" And there's already been a lot of ideas floated around during other people's talks and so on. Does anyone want to address that straight off before I use my prompts? No one has any ideas? Oh.
How much different discussion are you looking for compared to what we did yesterday?
Well, I mean, we did cover a lot of this yesterday.
Right.
So,
What's that?
It fits probably into each other.
Yeah,
That's the
right.
way to do
yeah, I mean, it's a soup. So,
It's a suit, okay.
well, okay, I'm going to leap ahead to one of my questions here. Do we want, okay, let's start off, since we have Kevin and Carl, who I presume are phased array feed proponents. Do we want to build a phased array feed? Do we want a larger KFPA? More elements in our focal plane array, or do we want something else?
Well, I'll just say that for the KFPA, you're limited to the number of, I mean, maybe 60 you can do. There's dual polarization, but the and you maybe get able to get dual polarization for what kind of elements you use, but you really are talking probably 200 or so in the KF with the phased array feed. So I think you need to start there. I mean, I don't really see that much advantage of a larger KFPA. You're not going to get the factor of 10.
I think you have more flexibility with the phased array feeds.
Okay.
Even though we lose a polarization.
Did anybody make a compelling case for polarization in the
No.
last few days?
I did. Well, no one spoke up anyway.
Yeah.
So just to be clear, it's not
Just
talk.
Yeah.
Still do polarization there. It's just kind of the first cut, but it would be more simpler if you did not. Polarization. It's not impossible technically.
I mean, now is the time for the polarization folks to make their voices known in this discussion, right? Argue for it.
So what's the science driver for these? What new science comes out that we can't do right now?
Do we need to build anything?
Yeah,
Eric.
so I think that's a good question. Certainly for K-band, the questions are what parts of the sky you want to map and what lines are we missing. I think that we all are on board with ammonia being the real workhorse in K-band for doing molecular ISM stuff. I'd be curious if anybody with a sort of view onto astrochemistry could speak to line polarimetry. Certainly it seemed to be a driving case for some of the NGVLA stuff I was looking into. But are there things like Goldreich-Hallafis effect or the sort of chirality, circular polarization arguments that could be accessed here. And I think that the question that immediately follows up that I'll ask is whether the sensitivity, like whether you get anything by averaging over large areas of the sky, because I think that that's the thing that a multi-band instrument would start to get you, is basically being able to synthesize a giant beam and get sort of average sensitivities that are quite strong, but over sort of, you know, quarter of a degree scale or something.
I mean, so for the chirality thing, everything that you presented, Eric, was correct as of 4 months ago. And then so a theoretician finally did the calculations for us for propylene oxide, and we need to have a polarization accuracy of a part in 10 to the 9%.
I think that's something you'll have to get into the technical specs sooner rather than later.
Right. For that particular molecule, which is fine, right? So, you know, more or less doing direct detections of chirality, at least for the molecule that we have, is out.
Sure.
So that answers that question, I think. I haven't had a chance to update that science case yet, but
It's all good. Yeah, I mean, well, okay, so I mean, maybe circular polarization doesn't seem deeply useful for the GBT science, but I think the linear polarization stuff would, I guess, also start to ask questions about continuum, and that's been, I don't know how well discussed that has been here.
Well, I mean, there was
Just-
Jaime, go ahead.
Yeah, just to follow up on those comments, we've been having some discussions between people interested in the ISM in general and more into the star forming cores. And one question that they would like to address at some point is to be able to get kind of a 3D version of the magnetic field on the galaxy. And for that, they would actually take a look at not mesas, but that they would take a look at Siemens splitting on OH, H1, try to extend a little bit the work from Crutcher. But also then at some point, you need to get to the core, to the innermost parts. And for those, some of the most interesting molecules could be either CCS. It's a bit faint, but if you integrate long enough, it's possible. Or try to do something like CN with Argus. But if you have, if you're going to replace the backend, it makes sense to have a backend that's going to work for more than just one of the instruments. And so in that sense, Siemens still is going to be an interesting topic, which at some point we'll have to really try to address. And unfortunately, some of the most expert members on that field are retiring. So some learning curve will have to be applied, and people will have to learn a lot of the tricks and things, like how to really process it to get a reasonable measurement. So, and in terms of if I would prefer KFPA or the phase array, it really concerns me if a limitation of the phase array is the spectral resolution. If the spectral resolution is only like 40 or 30 kilohertz, that's going to kill several of the key science cases for ammonia in particular. And I think that if that is not a major hurdle, then the other point I would like to bring up is that if you're going to spend a lot of time on doing some of the deeper mapping, doing only a few molecules per track, it's not very efficient. it would actually make a lot more sense to have different units that you could try to configure. So for example, in gas, we have like 7 molecules that if you only have 400 megahertz bandwidth, we would drop at least half of them. So we would drop at least half of everything that we mapped just because of the instantaneous bandwidth that you have from the phased array.
I think Kevin did say that there are multiple 400 megahertz we could drop across the frequency range, and that the 30 kilohertz was not a hard limit in any way.
Yeah, exactly. So you could, I mean, it's just, at least for the 30 kilohertz, that's more GPUs basically to get more resolution. That one's not a hard limit at all. And the same with the 400 megahertz of bandwidth, but of course it would cost more money. So
Just a comment about how would you set the number of pixels you want in either one of these devices? Is it, so I believe we're still anticipating, if all goes well, that the NGVLA will be having some presence here at Green Bank, which I'm hoping that's the case. I don't know if it's not. But but when that happens, then it would be the time when we could really do the great things, I think, because if you had a AFPA that had the same filling factor as the NGVLA, because they're small, we're going to basically need at least 10 times as many, or maybe 100 times, I guess, as many feeds to have the same beam. So you could start doing the mapping with the GBT and NGVLA in the same match, right? So that sort of sets the scale. If you're thinking really farther out, when the NGVLA comes, that's sort of my great desire would be to see, mapping it like in Green Bank. It'll be like at the 3 arc second level or something at FPA, because that's how the telescopes are within a kilometer of the GBT.
And you're talking about a separate array here.
Well, the NGVLA is going to be a separate array.
No, but I was going to, you were talking about
Well,
baselines
yeah.
here. I mean, they're talking about putting 3 NGVLA antennas here, so we'll be at the OBA station.
Well,
Still,
but
cross correlation with the GBT.
that's certainly the plan
NGVLA
at the
antennas.
moment, but I think by the time it gets built, it would be possible to do baselines here. If you have so then you can start to do the mapping at the 3 arc second level in Green Bank, because that would be, I think that would be helpful to the Maser folks, because again, it increases low noise a little bit.
Only 3 antennas, so unless we plug into the entire NGVLA, we don't have enough UV coverage to do it.
But the reason you have an advantage because you have 3 baselines, but you have all of the KFPAs is correlated, and it's giving you a different signal in each one of those correlations.
Like observing in there.
Well, if it's only 3.
That also requires having a correlator here.
Yeah, the correlator thing would be quite expensive to do that.
Yeah, I don't know. Kevin could whip one up in an afternoon probably.
But to amplify one's point, if you did have a focal point array or a KPAF, and you have the same field of view as the NGVLA, then Green Bank could be a zero spacing out the KPM observations with the NGVLA. That's not a bad thing. Right now, they're talking about the ALMA solution. You have a total power array. That's okay too. But I would rather, if I had my druthers, I'd rather have the collector.
Or in fact, have the total power array be here, because they went to smaller antennas, which is
They're going to put it where the 4 is, obviously, at the NGVLA side.
It'll be.
Because that's where they're.
Well, that probably is planned now, but I'm sure that's the best plan. If there was correlation with the GBT, then it's a big difference.
Well, I'm not disagreeing with that. It's just,
But anyway, so I'm saying that motivates the size of your KFPA, is what I'm saying.
Don't you need to make sure that whatever you found will have good continuum? Okay, because there is still the anomalous microwave emission, And I mean, if you built a really good continuum instrument, I don't know if that exists anywhere else in the world. And that would plug into the NGVLA as well, because even we still cannot do at ALMA with the total power array continuum. Right. Okay. It's just it's too expensive in time because you cannot match the sensitivity of the array. So this may be an opportunity to really build a fantastic continuum instrument. But again, I don't know the size of the anomalous microwave emission. I don't know what the good size case is for continuum at K-band to match NGVLA and continuum observations. But if we could build something that would actually try to solve the anomalous microwave emission, yes, it's spinning dust. Really, is it? I mean, how do we prove that? There is a case for that. Does that put the spectral line capabilities on the back burner? Can you do both at the same time? Can you build something that's very good, very good calibration accuracy for K-band continuum focal plane array, still have all the spectroscopic capabilities that you want as well? But this is where you come in, is like you would want the 100-meter dish to do continuum observations to complement zero spacing, and not just a total power array of 18 dishes, because you have to integrate forever.
Yeah, I think there's a lot of science opportunity in continuum, and we haven't seen a lot of productivity on it because there isn't a facility that's really operating here. There's some small dishes that are doing kind of cosmic microwave background cosmology oriented. There's an experiment at Owens Valley that's putting out some interesting papers here. But asking the question about the anomalous microwave emission, and also, like, this very quickly gets people who are doing CMB studies excited. If you're going to have high resolution continuum maps at, 20 to 30 gigahertz, that's something that they don't have. I mean, even down to 10 gigahertz, there isn't great stuff that's being done, and it's like it's challenging, but I think the fundamentals of the telescope are better. Like there's, I think we all appreciate that there's kind of a, tension with like what's, there's this other 100-meter telescope in the world, and they're doing all this continuum map, but like there's a great, like the optics are better at Green Bank and the environment is better at Green Bank to do a lot of continuum studies. So I think that there is sort of a science niche to be defined here. If it could be paired with spectroscopy, so much the better.
Dave pointed out yesterday that the CCB is, we'd have to somehow get close to that to make this worthwhile. Right? I mean, what's the case for that? Is there a case for that?
So I missed that. Could someone say that comment again so I can hear it?
So someone raised something similar yesterday, and Dave at the back of the room here pointed out that the CCB at Ka band is by far already our best continuum receiver. What can we do at K band that we can't do at Ka?
But you just need fast switching between two beams so you can beat the one over out.
I mean, there's, multi-pixel gives us faster, wider coverage.
Well, no, you need that fast switching to be able to do the continuum.
So do we want, what's the case for building a CCB at K band, right? Or can we even hook up the CCB to K? No, it's the cross-correlated feeds.
Question is, can you configure your K path to do continuum work at the same time as you can do spectral line work?
But it have to be in the same vein of the K, the vacuum will have to be there.
Yeah.
Let the monitor and do something similar to do CCB. How you get your stability. You can't have a detector in 3 kilometers away and expect to get the continuum stability. So that's the sole reason, that's the reason K is so good of a continuum receiver, because it's mounted very close. I mean, I don't know that you could couple off and sample it. I'm not sure what kind of, I mean, do you just want the whole band and sentence? You know? So there's a photon counter and the whole 8 gigahertz, or you want channel on, or what do you have?
Well, if they're doing continuum, they want a larger bandwidth, but I'm not sure if that works well with a phased array B because
Well, you form beams, but you have, you have the total bandwidth, amplifiers, and B. That's not the limitation. You don't have the illumination of the dish like you do with B. You got more spillover and beam, so you don't have a form beam, but you do have something that's collecting photon. It's not.
I guess, I mean, the bottom line question I think people are looking at is like, okay, for the science case right now is being driven spectral line work about basically. What would we have to give up on the spectral line side to get a continuum capable system, I guess is the question, and I don't know.
We come all down to the details. I'm not sure. It's just according on what kind of stability rafter.
Because the design
What
considerations are
the noise, the noise contributions from spillover, system temperature, you need all that stuff. Do analysis on that.
I mean, the best guess though is it would be worse.
Yeah.
Worst baselines.
Yeah.
Respectable
Yeah,
lines, probably
for sure.
yeah.
Like, if you wanted to do continuum, you would make a continuum back end like that, and you really would put it up the focus. And I mean, this is all kind of hard. Like, at least for me, I always like to think of it more science driven first. Like, what is the strong science case you're actually after? And then you just try and build the instrument that'll get that the best, and then everybody else, uses it if they can. But you know what I mean? And I think that's where we should be here is saying, like, I really want to map the entire galaxy and own it for there, and then build the instrument for that.
Then you want as many beams as possible. You go with single
Exactly. That's
polarization.
it. But like, for me, that's sort of the information I'm looking for. Is like, what is the one thing you would really want to do? You build the instrument for that, and then figure out how, if I would really destroy anybody else or not. Hopefully I don't ruin it for everybody else. Right?
So on this topic, let me ask that then. So we have the PI of ramps and the PI of Jaime, the PI of gas. I think he's certainly a representative of gas. So if we were to build a large KPA or KPAF, whichever, would you propose to do a full galactic survey? Jim's nodding his head here. Jaime? Would you write that proposal?
Like a galactic plane survey for ammonia. I'm not so sure. I think it could we would need to take a look what gives more scientific opportunities, because I think going deeper in larger scales, it could actually give, in some cases, more new opportunities than doing many more like shallow math. So that's why when you mentioned it before, I was thinking that if something like that is done, then it should be more like a tier, like a different tier. In some places you want to go shallow and fast, and in other places you really want to build up your integration time. And depending on what's available, then.
I agree with that. They're not mutually exclusive. It's complementary science. Right. So a galactic plane survey does not preclude you going as deep as you can on your favorite large clouds. I think both would be useful. Both could be done with this source.
Yeah, just making sure we're on the same page then.
Yeah.
So in that case, yeah, it sounds like a very powerful opportunity to create something like as useful as Glowstar or as useful as like VLAS.
It would be the equivalent of the CFA, CO survey or GRS or any of these.
Yeah.
Now, if Larry had asked me, am I interested in mapping 8 clouds super deep, I would say no, but he would say, that would be great.
But, we have Brent, something
I'm
in
just
mind?
gonna, if we're in the back room, if we can all like bump up the volume level a couple of times, the mics are further forward the room, so it's hard to hear.
I think Ron I saw something
Ron
pop
had
up
a
in the
comment.
chat.
Yeah, Ron added in the discussion, information about K-band CCB, as a dual feed receiver that uses correlation techniques to give around 14 gigahertz of effective bandwidth for continuum observing, and receiver stability for the current KFTA limits its effective bandwidth to something like 20 megahertz. And the TSIS is also better than KFTA. So just some more information.
Thanks. All right, so let's move it sideways a little. So the astrochemists have said that more bandwidth is what they want, right? So what do we do there? Do we need a new spectrometer? Is our cabling the limiting factor?
My understanding is that it's both.
Yeah.
The ion chains and the cabling are not allowed. Tony, someplace. There you are. You know better.
Yeah, Vegas is easily expandable. That's
Well, we just done
adding
it,
new
right?
nodes. But the big limit that's gonna be the toughest engineering challenge would be to update the IF system and the fibers to make sure we get all that bandwidth up to Vegas.
And so the limitation is with the converters, down convert, I mean, with the fiber optic links and KFPA bandwidth is all 8 gigahertz. You're limited when you reach the converter module and trying to, or the LO2 and trying to tune down to the baseband to be sampled. That's where the bottleneck is at 1.8 gigahertz. So, I mean, theoretically, if you added, for KFPA, you added 7 more fiber, 7 more IF chains, and you could get the full bandwidth of all 14 channels and had another way of sampling it or converting it to sampling frequency base.
So that's like hardware upgrades from here, between here and the telescope.
Well, it's in equipment,
Yes.
so it's not actually as difficult as it sounds.
There's room in there for that? Is there room in there for that?
Yeah. I mean, it's,
Doesn't sound very expensive.
It is.
It is?
Yeah, when they're looking at for Artist 144 proposal, it was 2 million. That
On the back end, but that was just because that was limited, that's why we picked 600 megahertz for that build us some back end.
Well, I mean, the first proposal we were looking at that makes the bandwidth wider. It's enhanced bandwidth.
what variant you talking about? That was driven by
Yeah,
just keeping the cost down on the back end. is all.
Yeah, because the back end would dominate the
It's
entire cost. If
cost,
you go
right.
with broad bandwidth for
Yeah.
100 broad bandwidth channels, it would be all back
So
end.
yeah, so it wasn't a technical decision, it was a cost decision, because we could build a back end off the shelf components that was relatively inexpensive per channel relative to the total cost of the project.
So Steve, so don't you want to just one pixel of KFA, just one, and you have as broad a bandwidth as possible? Is there a way to configure Vegas to do that?
8 gigahertz.
Yeah, so that, like I said, we have that mode, we have a broadband mode.
Is that what you guys use?
We use the broadband.
And we bring the problem, the bottleneck is up here. Is in, at the output of the fiber optic, we split the signal and you have to divide it into 1.8 sections and then stitch them together to get the total band.
So what they want is, infinite bandwidth. What
what would the maximum bandwidth practically be with the current receiver?
Well, it's limited way down, so it's 8 gigahertz.
That's just the operational range of the receiver.
Yeah, right. So it's feed and waveguide. So the feed is a corrugated feed that is used as circular waveguide and it's 8 gigahertz.
But theoretically, we could have all of those 8 gigahertz at once.
Theoretically, you can have all those 8 gigahertz. So it's not a receiver IF or, well, it's IF limited because we only have 8 IF. But it's the conversion and splitting and input to Vegas of an analog bandwidth is the limitation.
And sampling in the receiver room is just too noisy, you're saying?
Yeah, yeah, it's that could be done, I think. I mean, it's not practical for many channels, but if you're talking 2 or 4, it's in the realm of possibility. It's just the weight and power, heat, and RFI considerations. But the sampling rate, sampling speeds are getting higher and higher, and so theoretically you can move the sampling up to the front end with a few channels because you're real limited to heat dissipation and weight and RFI considerations. But it's not practical for a mini beam system, but for a few beams, if you just want a large bandwidth and really good stability, sample closely.
You still have to worry about RFI, which you need something like 100, 120 dB.
Yeah, but I'm saying you can do that.
It's doable, but
yeah, just a few channels. When you start multiplying that by 10 or 100, it's just that totally practical.
So one aspect we haven't particularly covered, Andrew, you said, your project was massively helped by having operator run observations. In terms of like system, the way we run things here, whether that's software or systematics and things like operator run observations, what can we be doing more there? I mean, I know Eric, for example, has done some pipelining stuff. Do we need a KFPA pipeline? Do we need more operator run things? Like, what are the thoughts there?
Yeah, I mean, you've heard all this stuff through user committee too, right? So yeah, all this stuff would be fantastic in terms of facility usability. I feel like, the idea of getting another gas or Keystone or ramp survey would not be challenging. Like, we have the infrastructure to deal with it. The hardest point where all of these science things break down is in the execution and finding people who will be on call to take shifts as they come up. So I think that these observations aren't like Argus W-band stuff where you have to really babysit the focus of the telescope and everything. Like, you can just run these. So having the operator driven operations would really facilitate I think general survey capabilities.
Pedro, what were you?
Oh, well, one of the things I heard was about the noise diodes. Just, well, I guess for the KFPA it's a bit different because they're variable, but just in general.
Across all receivers. Across all receivers.
Yeah, just in general, providing updated values for those things. And I don't know how much it drifts for the KFPA.
Well, worse than that. Well, I say worse. Yeah, separately to the fact that our noise diodes are not stable, not even designed to be massively stable. Go ahead, Tom.
They are pretty stable in time for all the receivers. There might be a very slow drift, but they are pretty stable. Yeah. So the reason that people think there are problems is, the lab measurements of hot cold load can only get was about 20%.
Yeah.
value, but on the sky, you're down around 1 or 2%. So there can be big changes between what you can measure on the sky versus what's measured in the lab.
Yeah, so the KFPAs tend to drift more just because they're not driven by noise diode, they're driven by FET, a hint, and those drift with temperature. We've known that's the reason we have a balance procedure, because every time you warm the receiver up and cool it back down, they reach a different value. But if you balance them often enough and keep the current at the specified level, they're quite stable and quite, the value is this 10 or 20% that we measure.
But, if we went away from these variable noise diode situation in KFPA to something fixed like we have for other receivers, it'd be much less of an issue. We brought up probably.
I will just point out, so I did a K-band project back in February that we struggled to calibrate, and I went back 10 years trying to find other calibration observations and found a handful. No one actually calibrates a K-band.
Well,
Maybe
certainly
they
try.
Be looking at a calibrator first to make sure you know what the noise diodes are.
And people don't, but maybe it's a chicken egg.
Well, I think the bottleneck that we always run into is that a lot of the obvious calibration strategies hit pointing concerns. And so, if you have the secondary swinging around a little bit, anything that you measure for point source stuff runs into just like, where are you hitting that within the beam? Is the wind blowing hard tonight?
So we're very much limited at the 10% level anyway by the wind and some other effects.
So I think that a relatively cheap approach may be to do a little bit more investment in on the sky calibration modes. Certainly we've collected some prototype data to try to really hammer this out and find out, like, can we, get the optimal calibration out of this? And, like everything, it's been time and personal bandwidth limited.
I can say that at least from our experience with gas, the values that we were getting for the aperture efficiencies varied by a fact, like 30, could be 30% off by default, but they were extremely stable over basically the whole period that we observed. So I agree, the stability of the noise diodes is very good. Is that we just we didn't know if the default value was properly measured recently, or if it was a value that got measured some time ago. I never got updated, because one of the issues I also see with new observers is that they assume that is up to date, and they assume that the calibration by default with the pipeline is accurate, and they don't even try doing any of the aperture efficiency estimates. So I think that's why also you don't see many people doing it, because they assume that it's under the hood.
This is kind of circling back to what we were talking about before, the operator-driven scripts and stuff like that. I think this might be a little too specific, but I will say, at least if we're talking about trying to make those kind of resources more available to more projects, making, I don't know, for larger scale, projects and stuff like that. Obviously our observations are extremely simple. They don't change over the entire semester. Basically, it's just point and shoot at one setup. The most we have to do is maybe change which setup you're looking at. If you want to ramp that up any further, I do think there are some things where it's certainly feasible, but I think it would be really, really handy to have more information accessible to the user in a programmatic sense from Astrid. So getting log outputs from, for example, when you're doing pointing and stuff like that, instead of, because right now it's the operator pushes yes or no and stuff like that. I think there's a bit more, like, just clearly map under the hood going on. It'd be really nice to be able to kind of easily access that from Astrid. I don't know what kind of lift that is, but I know that kind of stuff, especially if you're trying to get to more complicated observing, mapping or maybe stuff at high frequency, that's probably something that would need to be looked at.
Okay, so one thing one of the major reasons for this meeting is to give us direction, to get feedback from the community on K-band. So let's do that. Of the three things I've identified, could we get a show of hands on who, out of a new spectrometer or IF chain, expanding the number of pixels, whether that's, it sounds like that would probably be a KPAP, or whether we improve our operator run observation policy, for lack of a better word, or improve software in some way. Right? It's nebulous. So either sound off in the chat on Zoom, which of those you think should be our highest priority, or in the room, can we see a show of hands for the spectrometer and IF chain being the most important?
These are not all mutually exclusive.
And they're not mutually
and
exclusive.
They have vastly different expense. Well.
So I can take notes on everything everyone said as much as I like, right?
So you're just
at the end of the day,
This guy, who
Yeah.
wants more spectrometer is the question. So
So the extra counts, more or less. 5. I saw 5. Expanding the receiver and number of, getting more on sky coverage. You voted twice, you're not allowed to.
Well, I can have
No, you can do that. Okay. So, again, sorry, 5 again. Right. Okay, apparently we're. This may not be that. Okay, and then operator run observations, and pipelines, and so on.
I have a question.
just. 5 again. Okay.
Well, there's a lot of granular, like maybe having the operator, instead of doing RFI scans, do some cows, determining the cow values or something like that more regularly by.
Yes, that would be useful.
Because, for instance, I happen to know that you can do better with the GBT than you can with the VLA for calibration if you use the moon and K-band, because the moon gives you a super good relative intensity, and you can calculate the moon brightness pretty accurately, better than any of the AGN brightnesses. I wrote a memo.
Well, yeah.
But so that's a place where if you're using the KFDA for mapping, you should definitely be using the moon for that.
Brent?
So Eric put in the chat, are these all comparable costs?
Yeah.
Well, and they come from very different sources. If we were to fund a spectrometer or a new receiver, those would be mid-scale research, infrastructure grants probably, or something, whereas operator run, Jim, am I right? Am I saying anything wrong? Yeah. Whereas operator run observations and so on has to come from our operational budget in some way.
Are there any mapping programs that are operator run?
There have been. The
Not with the
difficulty
K-
comes
well, with
in,
the KFDA.
what happens if something occurs in the middle of a map? And that's kind of a science decision. You have to be prepared to be woken up for it.
Well, so breakthrough listen that's certainly our largest operator run project, and they have a hotline, and it's a very special case, but they have like a telephone chain, and people get called in descending order. So if you have a massive team, then it's quite straightforward.
Just a comment, Larry, I think you run the risk of spend all the money to build, big KFPA or KPAF or something like that, but you still have the tremendous amount of hurdles that you have in terms of calibration or pipelines or scheduling, constraints that people just don't have time or unwilling to observe or whatever. You could build a fantastic instrument, but no one's gonna use it for those same issues. If you do it the other way around, where you focus on, let's make a really good pipeline calibration, get things operated on, then you build up a community. It's be like, the potential barrier to get on is really, really small now. And now people be like, well, now we want more.
Yeah.
Now we want more capabilities, but if you put in the more capabilities and all this other stuff, it's still huge potential barrier to try to use it. You're not gonna bring it to community. So I would err on the side of, let's get these calibration things, let's get these pipelines going, let's get these operating, let's get this so well that the potential barrier to using them is so small that then people are going to want to ask for more stuff. Then you can put your $10 million into building something really great because they have the infrastructure in place ready to do to provide them fantastic products. Just my 2 cents.
And I'll throw something else out, kind of goes along with that. And these are just rough guesses at numbers. So if you build a new receiver, let's just guess it's going to be 5 years down the road before it's really operational. And in that time, if you map as deep as ramps did, you can get a degree an hour. You probably could get 200 hours K-band a year. So you can, potentially do 100 square degrees by the time you have a new receiver.
Well, and
that's not an insignificant chunk of the sky.
Yeah, that was actually kind of my first thing. So can we improve the time? Can we get more hours out of our current telescope through improved DSS or better surface or whatever?
Back in the day, Carl would put us on the telescope, just did marginal kind of, hey, give it a shot, see what happens. We took some pretty decent data. We made a lot of good detections back then, but there's a lot of stringency now where we're not on. But we gave it a shot. But then again, it was also the Wild West a little bit. We were here, we were messing around with things, and if it didn't work, we just gave it up to LBAT or something. But we really tried. As Jim said, you just integrate longer.
So is
But the PST is written so that you request total number of hours based on certain weather conditions, right? So that's why you schedule the telescope. Back in 04 or whenever we were doing this, it was just you guesstimated completely the total number of hours you needed because we didn't actually know enough to make that assessment. So I don't know.
I think it's you have to remember that like high frequency time isn't just used at K band, of course. There are other bands and other ambitions at like W band and stuff. And I think Dave Freyer once said that K band's almost harder to get than some W band time. So it's using limited K-band time with expanded instrumentation makes sense, provided the science is there for it. I'm quite sympathetic to the point that by the time you build a new receiver, you could probably get a couple hundred hours of additional K-band time with the existing facility there. And so I think a lot of these questions really come down to costs and timelines and everything. So it seems like doing hardware on the telescope would be probably the most expensive and longest timescale solution to a lot of these things when you could get a lot of gains through other things kind of now and less expensively. So that's sort of, it's hard to answer a lot of these questions without a real cost benefit.
I think the question, so obviously these single beam pointing things really would benefit from a lower system temperature, but already K-band's great, right? So is there what's the best that can be done? Another 10 Kelvin reduction? It's 35 Kelvin.
Well, yeah, this is it. I don't think we can improve our sensitivity massively. Yeah. Jim says not a factor of 2. We need to be looking elsewhere.
Well, factor of 2, of course, is 4 times as many beams.
I think we're getting close to wrapping this up. Does anyone else have anything they would like to bring up?
Yes. Go ahead.
I think someone else spoke up at the same time as I did. I don't want to grab the floor.
You go first.
Okay.
Go ahead, Carl.
This has been kind of a reverse panel. I'm the audience listening to you all, so thanks for the good discussion. I guess if I were to write a newspaper headline summarizing my very simplistic view of what's been said is you have a world-class telescope that becomes a better continuum survey instrument with KPAF.
Yeah, I don't think there's any shortage of ideas. I think Eric's point of, you know, without a cost benefit analysis, you know, some actual numbers here, maybe it's very hard to make this beyond go further than a hand wavy argument.
And maybe I'll dangle just one more little idea. You know, the cost for a full-on K-band phased array feed from front end to signal transport to a, you know, really wideband digital back end would be, you know, on the order of millions. But, you know, there's a low cost approach. If suddenly a magical science problem were to appear where we just needed more survey speed, a wider field, you know, I can envision doing a planar K-band phased array feed with mimic amplifiers, you know, traditionally soldered on the back using PCB fabrication techniques, the whole thing behind a vacuum window with a thin sheet of foam to support the weight, cables back, and then the alpaca signal transport and back end. And there's a wide field K-band phased array feed at, you know, modest cost.
Jim, you were.
Yeah, I wanted to thank you, Larry.
Thank you.
Thank you for organizing and hosting.
Thanks. Yeah, so we're going to wrap up the whole conference on that note. Thanks to everyone who made it here in person. Thanks to everyone for calling in on Zoom every day. I know staring at a Zoom screen for a few hours a day isn't always fun. So yeah, so thanks for your contributions.